Hello, I'm Frederic Magniez, and I represent the first and the last part of this talk.
Hello, I'm Ashwin Nayak, and I'll present the middle part of this talk.
The main motivation of this work is the study of distributed computing in the quantum setting. In distributed computing, we usually have a collection of processors. Some of them can communicate together, and all of them would like to solve a common task. For instance, they would like to learn the structure of the unknown network, or they would like to parallelize some hard computation using their collective powers. Another motivation is the study of cloud computing, where data is replicated in many data centers, and the client have access to the closest center. So let's start with the distributed setting. The very special case of two parties, two computers, is known as communication complexity. Here, the input is distributed among the two parties, and they would like to solve some task while minimizing the total communications. There are many applications, essentially for proving lower bounds for many models of computation, including distributed computing, but also streaming algorithms. So let's generalize a bit this model to a more realistic setting. Imagine the two parties are very far away, so probably they need a communication channel with many repetitors. Those repetitors can be seen as processors. So we have a very simple distributed model of computations. The input is on the extremity of the line, and on the line of the channel, there are many processors. Let's say there are D+1 processors. So on the negative side, there is a delay, of course, because of the distance between the extremities. But on the positive side, maybe those processors could help to speed up the communication. So let's study this model on a very basic but yet fundamental problem called set disjointness problem. So here, each party have access to a n-bit strings, and they would like to find a position where they together have a 1. It is like finding a common slot in an agenda. This problem is very important in communication complexity. It's a kind of analog of a Co-NP complete problem. Many lower bounds rely to the hardness of this problem. Indeed, classically, even using randomness, basically each party needed to reveal their entire string because they need to exchange a linear number of bits in the input size. Quantumly, we can do better since only a square root in the input size number of bits is enough in order to solve the problem. So let's see what happened on a line of D+1 processors. So now the input is at the left and the right of this line, and all the processors can simultaneously communicate each other by exchanging a small message. This is known as a congestion restriction. This message could be either of random or quantum bits. So let's see what happened at the first round. Each processor performs local computations. On the extremities, this computation can depend on the input. Then, processors can exchange a small message with their left or right neighbors. This is the end of the first round. At the beginning of the second round, each processor can now make a new local computation using the message they received, and for the extremities, using the input X or Y. Again, after this computation, they can exchange a message. And this continues like that. The distributed complexity of the problem is then the number of rounds required to solve disjointness. So let's see what we can say about this problem. So first, in the random setting, when the message and the processor are classical, but they can use randomness, using the result from communication complexity, that is when there are only two processors, we know that disjointness requires a linear number of rounds. Since we assume that the distance is at most n, we can achieve this bound just by sending x from the left to the right. And in fact, there is a very nice reduction from this problem to the one of computing the diameter of an unknown network. In this problem, now we have n processors. They are in an unknown graph, and they together, distributively, would like to compute the diameter. Then it has been shown that a linear number of rounds is also needed, and this is because of reduction to disjointness. So in the quantum setting now, what do we know already? Again, because of communication complexity, we already know that disjointness requires a square root of the input size number of rounds. So with François Le Gall, 2 years ago, we shown that in fact on the line, disjointness can be solved using a number of rounds which is the square root of the input size n times d, the distance between the extremity of the line. And this result is optimal when processors have an additional constraints, namely a very small memory, a polylogarithmic memory in the input size. But this constraint is not usual in distributed computing. And this is the starting point of this work. What happens if we remove these constraints? Ashwin will show you that it is possible to establish a stronger lower bound than the square root of n, which is already known, when the distance d is large enough. Namely, there is an additional term, which is the qubit root of n, the input size, times d squared, where d is the distance, without any limitation on the memory of the processors. As is the classical case, we have as an application a lower bound for the complexity of computing the diameter of an unknown graph. So if delta is that diameter, then the number of rounds for a quantum distributed protocol to compute this diameter delta is at least square root of n, because of the lower bound on disjointness, plus qubit root of n times delta square, where delta is the diameter we are looking for. Note that this bound doesn't match the complexity of the best quantum distributed algorithm we know, which is square root of n delta.
To show our lower bounds, we consider a reduction similar to one introduced by Le Gall and Magniez. This reduction relates protocols on the line to two-party protocols, for example, for set disjointness. Let's look at a simpler case where it's easier to understand what the simulation looks like. Here we have a line with 5 processors, so D equals 4, and protocol that runs for 8 rounds. The parties A0 and A sub 4 are given the inputs X and Y respectively, and in each round, each party exchanges polylog n qubits with each of the neighbors on its sides. We simulate such a protocol with a two-party protocol as follows. Alice, the first party, gets input X, and Bob gets input Y. From here on, Alice tries to simulate the actions of as many of the parties as she can for as many of the rounds as she is able to. In the first round, Alice can simulate the actions of A0 because she has the input X, and she can simulate A1, A2, and A3 because those processors do not need knowledge of either X or Y to complete their actions. A3's actions in the second round now depend on Y because of the information received about Y from A4. But Alice can still simulate A0, A1, and A2. Similarly, in the third round, she can simulate the actions of A0 and A1, and in the fourth, the actions of only A0. Effectively, she simulates the top left upper triangular region demarcated by the thick green line in one round of the two-party protocol. Then she sends the memory of all the parties A1 through A3 and her message from the fourth round to Bob. Now Bob can complete the actions of all the parties A1, A2, A3, or A4 from round 1 to round 4 that were remaining, meaning not completed by Alice, all on his own, since he has all the information and the space on which these actions are conducted. Having done this, he then returns the memory of A1, A2, and A3 along with his message from round 4 to Alice. This completes the simulation of D rounds of the line protocol in 2 rounds, that is 2 messages of the two-party protocol. Continuing this way, they can simulate a block of D rounds of the protocol on the line with 2 messages of the two-party protocol. In effect, we can simulate a protocol on the line with R rounds with a two-party protocol with 2 times R over D rounds and communication essentially D times the memory size per round. Since we know that any M round protocol for disjointness in the two-party model has communication at least essentially N divided by M, assuming that the parties A1 through AD-1 that are not at the extremities have limited memory, that is memory polylog n, we can conclude that the round complexity of the protocol on the line is at least square root of nd, up to polylogarithmic factors. Now, does having larger memory give any advantage? We show a similar polynomial in n and d lower bound even when the memory may be unbounded. For this, let's go back to the two-party simulation that we designed. The key observation here is that the memory held by A1, A2, and so on up to A sub d minus 1 does not really reflect the amount of information they have about either input. In each round, they receive at most polylog n qubits of information from either party about the respective inputs. Since we simulate d rounds of the protocol on the line with 1 round of the two-party protocol, the additional information that the memory of all the intermediate parties contains is d polylog n. We can formalize this using a notion that was introduced by Jayan, Radhakrishnan, and Sen in 2003. The quantity is called information loss and is denoted by IL pi given x, y, and z. Here, pi is the protocol in question, x, y are the random inputs given to Alice and Bob respectively, and Z is a random variable that's correlated with X and Y. The quantity contains a term for each message in the protocol. Let's say that just after the message in the kth round has been sent, A sub k denotes Alice's registers in the corresponding state, and similarly B sub k denotes Bob's registers in the corresponding state. Let's say Alice peaks in the odd numbered rounds. Then the term corresponding to the kth message, where k is odd, is given by the mutual information of X, which is Alice's input, and the registers B sub k and Y that are held by Bob, given Z. There's a similar term for each message for k even, which are sent by Bob. Each of these terms in the information loss quantity can be bounded using the intuition we had previously described. Namely, we can bound the terms by k times d polylog n for each k, provided the inputs x and y are independent given z. For this case, we can bound the information loss by m squared times d, essentially, where the two-party protocol has m rounds. So starting with an R-round protocol on the line with D+1 processors, we get a two-party protocol with 2 times R over D rounds and information loss that is bounded as essentially R over D squared times D times polylog n. At this point, we simply invoke a result that was implicit in the work of Jain, Radhakrishnan and Sen that was previously mentioned. They showed that there is a special distribution over inputs x and y correlated with random variable z, such that x and y are independent given z, and for any m-round two-party protocol pi for set disjointness on n-bit inputs, the information loss is given by n divided by m. If we combine this with the properties of the two-party simulation we derived, then we get that the round complexity of set disjointness on the line is given by the cubic root of n times d squared. And this completes the proof of the lower bound.
In order to understand the limit of our method, we are going to study a related model connected to cloud computing. In these settings, we have a remote server that hosts our data, and a client is going to query its data. So this model and related complexity is called query complexity. It's a very simple view of cloud computing. Given some task, the goal is to minimize the number of queries to the servers. Again, this model has many applications, essentially for proving lower bound. For instance, when we say that sorting an array of n elements requires n log n comparisons, this is query complexity. So let's now move to the case of two servers. Imagine the client has access to the closest server. When he wants to access to the data of the other server, he has to move to that server, implying a delay due to the distance. We call that the switching delay, given by some parameter d. So if we compare with the previous model of the line of processors, the input cannot be accessed simultaneously on the left and on the right. But when we access the input, we always have the full memory of the client. So let's see what happens if we go back now to set disjointness on this model. So the query model is simple. Given a bit position, let's say I can either get the I bit of x or the I bit of y. And we are going to measure the total number of queries we make to x and y. But when we switch from x to y, we give a penalty of an extra d queries. Any other resources, like time and space, are unlimited. And again, I assume here that d is less than n, otherwise the problem is too easy. Classically, even using random queries, we cannot do so much than querying the full input x and y. Indeed, disjointness requires a linear number of queries with switching delay d, and the lower bounds come from a lower bound of query complexity for OR. In the quantum setting, this lower bound becomes square root of n. In this work, in fact, we characterize the quantum query complexity with switching delay of disjointness. It is either square root of n or qubit root of n d squared, depending on the value of d. So the lower bounds, in fact, come from the techniques Ashwin presented, and the upper bound is a matching algorithm using quantum rules. So this model can be seen as an example of the limit of our method, since we cannot make any difference between the line of the processors and the query complexity with switching delay for establishing a lower bound. So let's look at the algorithm. So first I'm going to give a classical description of the algorithm, and then I will quantize. So this is a standard way of designing quantum algorithm. Let's assume here that the distance, so the switching delay, d, is fourth root of n. So I'm going to describe a random walk of a Johnson graph. More precisely, we start with a random subset of square root of n positions, and we are going to query x on those positions, so the cost is fourth root of n. Now we are going to check those positions with y. So we move to y, and this has a cost of fourth root of n because the distance is fourth root of n. Now we query also y on I in order to check if they have a 1 in common. This cost, therefore, again, fourth root of n. Maybe we found a solution, meaning I where both x and I has a 1, but maybe not. So we have to look for another subset I. For that, we go back to the left, and this cost, again, fourth root of n. Instead of just taking a new subset, we are going to replace at random, one by one, the element of I. So one can show that if we iterate enough time, meaning square root of n times, we are going to get a new random subset I, because the mixing time of this walk is square root of n. So the extra cost is again square root of n. And we go back again to the right and we iterate. How many times do we need to iterate? We have just to look at the success probability to get a position where both x and y agree on bit 1. And this success probability is just 1 over square root of n. So we just need to iterate square root of n times. Therefore, the final query complexity is n. Let's go to the quantum case now. The first step doesn't change, except that now we are going to take a quantum uniform superposition of subset. For the second step, we are going to use Grover search. This gives us a quadratic speedup. For the third step, quantum walk makes also quadratically faster. We again have a quadratic speedup. For the last step, we just use quantum amplification, which implies that we just need to iterate quadratically the inverse of the success probability. So the final query complexity with delay d is just square root of n. To conclude, we consider two models of computation. The distributed model on a line of d processors and the query complexity with a switching delay d. For both models, we get the same lower bound, so we cannot distinguish the two models. we have a matching upper bound for the query complexity with switching delay, but there is still a gap with the complexity of the best known algorithm for the processor on the line. As an open problem, of course, we would like to understand what is the actual complexity of disjointness on the line, and more generally, what is the distributed complexity of the computation of the diameter on the quantum networks. Thanks for your attention.